Okay, welcome everybody. Hope you're doing well today. Let's begin. So you have a homework assignment that's available right now on Blackboard, homework 1. And that's covering some of the concepts that we've addressed so far on Monday and Wednesday, and then also some of the things that we'll continue with today. It's due on Wednesday, and we don't have class on Monday because that's a university holiday. So I don't plan to be on campus on Monday, but I do have my phone with me, and Microsoft Teams is on my phone, so that if you give me a call on Teams, there's a good chance I'll pick up. One thing that Teams isn't very good for, though, is there's a chat feature, and I just don't see those messages. And so either email or call me in my office or give me a call on Teams, but the back and forth texting chat feature on Teams just kind of falls into the background. So, any announcement related questions before we begin? Okay, so we're talking about resistance to flow. The fact that when water flows through a pipe, the pressure is decreasing in the direction downstream. For a horizontal pipe, that somehow the interaction between the fluid and the pipe itself is extracting energy. There's energy loss as the water goes through that conduit. And there's lots of different ways that hydraulic engineers can account for the rate of energy loss. One of the older equations that was used a long time ago was the Chezy equation. And the Chezy equation was derived from the observation that the slope of the energy grade line and the hydraulic radius could be correlated with some friction factor, and then combined all together, those three variables would explain the velocity of flow through a pipe. And so what they did was empirical measurements, where a series of researchers would make a measurement of what's the slope of the energy grade line, the roughness of this pipe material, the velocity, and from the measurements they came up with roughness C values. And the C values that went into the Chezy equation would be on the rough end, low numbers, and on the high end, smooth numbers. So that you could see if you had a high C value, then that would give you a larger velocity for a certain slope of the energy grade line. And it's important to just understand the basics of this relationship, because although we don't use the Chezy equation any longer directly, because we have an improvement in the Manning's equation, the same foundational ideas are there, that the conduit shape, the slope of the energy grade line, and some factor that characterizes the roughness can be used to give you the velocity of flow. So the Chezy and the Manning's equation both can be used in closed conduit flow. Manning's equation, though, these days is most often restricted to open channel flow. It's not often used in closed conduit pipe flow. So we'll use Manning's equation a lot in the second half of the semester. So page 201 of your book, I just want to draw your attention to this equation, because sometimes you may be asked to relate a Chezy C value to the friction factor F that would go into the Darcy-Weisbach equation. And so here is an estimation of how you could relate the two. It's an approximation. It's not direct, but it does exist. So you'll remember back to fluid mechanics when we introduced the idea of a velocity distribution. And let me just refresh your memory that in a flow through a pipe, the velocity of flow is the largest in the center of the pipe. And near the edges, where the water is in contact with the pipe material, the velocity is the lowest. And in fact, if we zoom in on just that molecule of layer that's directly adjacent to the stationary surface, that molecule of water that's just right at the border isn't moving at all, because of the no-slip condition, which says that a viscous fluid can't have a frictionless movement over a surface that has roughness. That because of viscosity, the fluid will adhere with the same velocity as that stationary surface at the boundary between the two. And then the further away you get from the border of the pipe, the velocity goes up. So this figure is showing the velocity profile. A parabolic profile is characteristic of laminar flow, where the center of the pipe would have a velocity that's double the average velocity. And then in turbulent flow conditions, there's a logarithmic shape where at the edges of the pipe the velocity is very low, tapering to zero. But then there's relatively flat average velocity across that profile. And at any given instant, in the case of turbulent flow, maybe at one spot the velocity is low and at another it is high. So over the temporal average, over some time period, then it would average out to a flat nose in the logarithmic fully turbulent flow profile. But at the top of the pipe, at the bottom of the pipe, now really what it is it's circular, of course. So all that you think about this, it would be bullet shaped in the case of a parabolic. And so try and think in 3 dimensions what that would look like. And of course, Reynolds number can be calculated with the velocity times the diameter divided by the kinematic viscosity. So we have different profile depending on the flow conditions. Now, this is a new slide that's not in the notes. Have any of you gotten the notes so far off a Blackboard? Okay, so they are visible on your end. There have been a couple of hiccups this semester so far with the transition from the old version of Blackboard to the new one, but I'm glad that you're seeing the notes now. This slide isn't in the notes. This is something I put together just this morning as I was thinking about how can I help to explain a little bit better on what a boundary layer is. So I went and found this image online, and I'm going to walk us through a discussion of what a boundary layer is by posing a hypothetical. So let's say that we have water that's flowing, and before the water is encountering this stationary surface, you can see that the velocity profile is flat. That, up here at this elevation, the velocity is just this initial velocity. At the bottom of the profile, it's the same. So it's a flat profile. We have uniform flow. Uniform flow meaning that there's no variation in the direction of flow up to this point. So this would maybe be in a river that was flowing sideways. If we didn't go very far down, so we're not encountering any effects from the bottom of the river, and if we're not right at the surface, because there is a little bit of friction effects that occurs as the air is stationary and a river is moving. So we're just into the depth of flow, or somehow we had like a synthetic flow field that we were able to prepare. You maybe would remember the laminar flow video that I showed you in fluid mechanics last semester, where it was showing like an arch of water that was like really smooth flow, and it almost looked like it was not moving at all because there weren't any bubbles and the diameter wasn't changing. So here we have just kind of uniform conditions, and then the flow encounters, think of this as just a sheet of metal maybe. So what would happen is, because of the no slip condition, the water that is in immediate contact with this stationary surface stops. And this dashed line represents the boundary between where the conditions are influenced by the stationary surface and not influenced. So the no slip condition at the surface of the stationary material means that a shear stress is being applied to the fluid. So if we go further and further downstream from where the contact begins, then the thickness of the boundary layer is increasing, but it looks like it's approaching some limit where it's not going to continue to get longer and longer. It's going to reach an equilibrium. Now, what this diagram is showing is the velocity profile as a function of how far up and away are we from the surface at which is applying shear stress to the fluid. So down here at the bottom, the velocity is lower, and the further away you get from that surface, the velocity is increasing. So this boundary here is where the velocity is below it 99% or less of the free flow velocity. And so beyond this, the velocity is 99% up to the free flow velocity itself. There's different definitions for the boundary layer, but here in this representation, let's just assume that this border is saying that anything that is under the influence of the surface is going to be slowed down a little bit. How much is a little bit? Anything from 0 to 99% of the free flow velocity. So that's a pretty generous description of what is under the influence of that surface. Any questions so far? Okay, let me ask you a conceptual question. What if this velocity increased? Think about what would the shape of this boundary layer look like if suddenly we sped up the velocity of the water that's approaching the surface. I guess there's three options. The boundary layer thickness would stay the same, it would get bigger, or it would get smaller. Just try to think for a moment, what does your instinct or your intuition tell you about how thick would that layer be, the layer that is influenced by the stationary surface, if the velocity upstream was increased? It would get smaller, that's right. And so what led you in that direction?
I assume more power would make the stationary surface have less of an effect.
Right, so you can almost think about it, you know what blades of grass look like as water's flowing over it, right? Just think about if blades of grass are sticking up and water's just moving slowly, then they tip over a bit, but when the velocity increases, then those blades of grass are going to be pushed down with more force. And I think that there's probably an analogy between that and this, is that the thickness of this boundary layer depends on a variety of things, including the magnitude of the upstream velocity. So in the vicinity of the surface, the fluid velocity decreases, but then it's coming into an equilibrium. As we go downstream, eventually, like this stops changing and it flattens out so that how much of the thickness is under the influence of the shear stress exerted by the surface on the fluid is known and could be calculated or measured. And so a certain portion of this, so think about what this means. This is the velocity. So the velocity of the water down here is 0. I'm pointing at a water molecule right now at the bottom. 0 velocity for the water. We go a little bit further, the velocity is moving it's moving slow. Further away, it's moving faster. The further away you get from the surface, the velocity is faster and faster. So what we had said earlier was that our definition was going to be where the velocity is less than 99% of the free flow velocity. A certain amount of the water that's above that surface is going to have laminar conditions. Even if the bulk flow inside of the pipe or in a river, even if most of the water is turbulent, because some of the water is close to the stationary surface, it's moving slow enough that there could be a region where the conditions are laminar. So does that make sense to everybody? Remember, laminar conditions are those which are associated with low velocities, where the flow is smooth and quiescent, where we don't see turbulence. There aren't eddies or like the swirling countercurrent flow vortices. It's just the water's just going in a normal direction. Remember back to the lab, that blue dye that we were injecting into the Osborne-Reynolds apparatus. Remember the blue dye, and when the velocity was slow enough, it just kind of stayed together as a stream. But then as we opened up the valve and the velocity increased, then it was being mixed. So there's a certain layer in the region immediately above the pipe where conditions are laminar. That's a preview of the next slide. But before I move to that next slide, any questions about this one or the things that we've been discussing? So we've already addressed what would happen if you increased or decreased this upstream velocity. If you increase the upstream velocity, the boundary layer thickness, in terms of how far away from the surface do you have to go to see that 99% of the free flow would get smaller if you increase the velocity, and if you decrease the velocity, then the boundary layer would get thicker. Okay, now this is a different figure, and one that I hope you've got the book, and the book has a reinforcing discussion about this figure that I think is important to spend a little bit of time thinking about after class today. I'll talk about it now, but this is one where, in my experience, we just don't have the time to get all the way to full comprehension and comfort to get together. It may be the sort of thing where you have to hear about it from me now, and then also revisit it later, and then finally it'll sink in and click and make sense. So just an invitation to do that. Okay, so this again is similar to the kind of diagram we've looked at before, where water is flowing from the left to the right, and here at this location it says it's the center of the pipe, and then we are here at the edge of the pipe. So this is a graph of the shear stress in the fluid as a function of distance from the edge of the pipe. So this axis is down here at the bottom of the pipe. And so it makes sense that the most shear stress in the fluid is those molecules that are just right above the stationary surface. So it's like the influence. I don't want to call it a force field, but this stationary pipe is exerting a shear stress, like a resistance, on the fluid. So up right at the border between the metal and the water, that's where the resistance is the highest. But then the further away you get from this bottom aspect of the metal, the shear stress is decreasing. And so that makes sense why the velocity would be highest at the center of the pipe. This is just kind of graphing for us how much shear stress is exerted on the water as a function of the distance from the center of the pipe. Now what this is showing is that there's some boundary layer, and we're going to look at a couple of formulas for how to calculate the thickness of that boundary layer. Now there's a lot of different types of boundary layers. There's a velocity boundary layer, which is what we talked about here, the idea of the 99% border. There are thermal boundary layers. So think about your skin and how much colder it is when you're standing in the wind. And the reason why it feels cold when you're standing in the wind is that the warm air that's in contact with your skin right now is getting blown away. And the thickness of the boundary layer is smaller when you're standing in a stiff wind. And so there's thermal boundary layer, velocity boundary layer. We can also think about in terms of how big is the cushion that is laminar. And that's going to be an important one for us. Is like how far from the bottom of the pipe upward is the conditions laminar. Remember, laminar is any Reynolds number that's 2,000 or less. So if the water's moving really fast, then it could suppress the thickness of the laminar sublayer. If the velocity is moving slowly, then the laminar sublayer may be relatively thick. And if the water's moving really slowly, then the entire pipe may have laminar flow. But even when conditions are turbulent, like when we had that, remember back to the lab last semester, injecting the blue dye? So the water was going down, and the blue dye was going everywhere. It looked like it was going everywhere, but it wasn't going really close to the edge of the pipe. Because in the outside edge, there was that layer that conditions were laminar. Even though the rest of the pipe, most of it, was turbulent, there was this cushion around the outside that was a laminar sublayer. So we're going to look at some formulas for calculating the thickness of the laminar sublayer. And so the takeaway message from this is just the distance that shear stress is exerted, depending on, for example, if the bulk flow is turbulent or if the bulk flow is laminar. Obviously, if you have higher velocities and there's turbulent flow, then the shear stress is going to extend further into the pipe. Any questions about the things that we've been talking about so far, the idea of a laminar sublayer? Any questions about that concept? You know, we're kind of approaching two things simultaneously. We want to have a fundamental understanding for like the background physics that's happening that governs the movement of water. We want to understand kind of the main high-level concepts at the same time that we're using empirical equations that help us to estimate things. I don't want to just teach you the equations and then not have you understand why they're set up a certain way or why they behave the way that they do. I think you have to be able to apply the equation and also understand the background there. That's engineering. Technicians just do the application, but the engineers know the foundational science and math and also perform the application. Okay, so the laminar sublayer thickness depends on the degree of turbulence and the roughness of the boundary. So the pipe materials, in other words. If you have a rough pipe versus if you have a smooth pipe is going to influence how thick that boundary layer is. Now here's the relationship that if the flow velocity is going fast, then you'd have a high shear stress that's being applied, but it would lead to a smaller laminar boundary layer. We'll look at the Morrison-Wigert criteria equation in a moment, and you'll see that relationship between high shear stress and smaller boundary layer thickness. Again, this is consistent with that mental image of fast-moving velocity pushing over grass that's growing at the bottom of a channel. Fast velocity, that portion of the fluid that's moving slowly, that's right in the close proximity to the bottom of the channel, would be small. Whereas slow-moving velocity leads to a lower shear stress quantity, which we're going to see gives you a larger laminar boundary layer. Remember, there's lots of different boundary layers. There's thermal, velocity, and then looking at things in terms of their Reynolds number. So we're talking here about the laminar boundary layer. Okay, so roughness. I mentioned here that the roughness of the boundary is part of the equation, part of what's governing. So our textbook and other sources as well characterize different materials in terms of their equivalent roughness. Here, the variable that's assigned epsilon. Other texts call it K sub s. But what it is effectively is if you had a grain of sand that is glued to a pipe, and in fact, we have a pipe with a bunch of grains of sand glued to it. In the pipe rack, you remember that bottom pipe that you didn't use in the experiment last semester? You just used the top 4 pipes. Those top 4 pipes were stainless steel, and the one on the bottom has sand glued to the outside of it. So if we measured the grain diameter of that sand, and we knew what the equivalent roughness was, we could use that as a measuring stick, so to speak, of equivalent, like trying to relate other materials to how rough they are to what is the equivalent sand grain diameter that would be glued to a surface. So for example, glass is so smooth that if you were going to try to find an equivalent smoothness of glass, the diameter of the sand grains would be very, very small. In contrast to that, cast iron is relatively more rough. Look at the diameter is so much larger than glass. And so cast iron has a crystalline structure, and the outside of it is a little bit grainy. And because of that, because just the inherent characteristics of the mineral, there's a roughness on the outside of the material. So you can see that everything from concrete to corrugated metal. All these things have been expressed in terms of equivalent roughness, and we can have it either in SI units or traditional units. And this is a table that's available in your book and also in the notes. And it's something that we're going to use. It's funny to think that there's pipes made out of wood. I guess it's similar to a barrel. You know, they use barrels for wine or whiskey, but a long time ago, and still I think there's a few quaint old places that have these fitted wooden sections, sometimes with metal coil around the outside just to keep everything together. So wood stave I don't think will come up very often in your engineering practice, but somebody went to the trouble of characterizing the roughness of a wooden pipe. Okay, so I earlier mentioned the Morrison-Wigert criteria, and here it is. This equation is trying to estimate how thick the laminar sublayer is depending on the amount of shear stress that's applied. You'll remember from last time we talked about how shear velocity is just another representation of shear stress that ends up having units of meters per second. That's why we call it shear velocity. Is just, you know, we've done a transformation of shear stress where we normalized for the density of the fluid, and lo and behold, it gives us units of length per time, so we called it a velocity. So this Morrison-Wigert criteria says, take into account the kinematic viscosity of the fluid and the magnitude of the shear stress that's applied, and then that will tell you how thick this laminar layer is. Now, if the thickness of the boundary layer is more than 1.7 times epsilon, so that means you've got a really thick laminar sublayer. So in that case, the thickness of the laminar sublayer is much larger than the roughness elements. So you can think of this as like mountain peaks. These little peaks are meant to represent the pipe. And so if this was cast iron, this is kind of the undulations and the grains and the roughness of the cast iron itself. If the laminar sublayer is completely submerging this, then it's going to have a different effect on the flow compared to if those roughness elements project into the turbulent zone and aren't completely cushioned by the laminar zone. So if it's greater than 1.7 times epsilon, we call it hydraulically smooth. And if it's less than 0.08 times epsilon, then it's hydraulically rough. And of course, that leaves a pretty wide range where we're in a transition zone. But this is just trying to characterize why, for the Moody diagram, we see certain parts of the Moody diagram are flat and certain parts of the Moody diagram are curved. It's because different effects are taking over as the shear stress increases. Now we'll talk about this, we'll continue the discussion. There are a couple equations we'll learn on Wednesday that allow us to estimate the friction factor F, so we don't have to use the Moody diagram. Sometimes that's not real convenient, the Moody diagram. So we'll learn some quantitative approaches to calculating F. But this is just a way of understanding what's happening depending on the thickness of the layer. So water that's flowing on this top case, it doesn't really even know about this roughness because it's fully submerged in the laminar layer. So it has less of an influence than if the roughness elements are projecting into the turbulent zone. And remember, in the turbulent zone, there's all this swirling and eddies and chaos. And so when you have that turbulence encountering these roughness elements that are projecting into the turbulent zone, then the friction effects are going to be different. Okay, so does that make sense? The idea that you'd have a different effect if the roughness was cushioned versus projecting into the turbulent zone? All right. Now, let's change gears a little bit, dust off the calculators, and crunch some numbers here. So I've got an elevated tank. Let's see. You're going to have to calculate what is the water surface depending on what we want to be able to do. We want to deliver a pressure of 350 kilopascals to the ground floor of the building. So here you'll see that our datum is the bottom of the tank, and we're saying that the ground floor of the building is 20 meters above that. And we want to have a pressure of 350 kilopascals at the bottom of the building. So we're going to be substituting some things here into the energy equation, where at location 1, which is in the tank, the fluid will have no pressure, it'll have no velocity, but we're just calculating for Z1 as the unknown. And then here at location 2, which is at the bottom of the building, we know the elevation, we know the pressure that's required is 350 kilopascals. As far as the velocity, I'm going to have to remind myself, but I think in this case, probably we would ignore the velocity effects unless we're just fixated on precision. Oh, and it looks like in this example I was fixated on precision. You'll calculate what is the required velocity. Let's see. So 1,200 liters per minute, and the pipe diameter, you'll be able to calculate V from that. So what I'm getting at is V2 isn't canceled out. Calculate the velocity through the pipe and include that in V2, because the unknown in the energy equation is going to be Z1. We're calculating what is the elevation at 1. And for the head loss due to pipe friction, calculate the head loss due to pipe friction with this H sub F formula. And let's see, what else to mention in advance? We know the friction loss is given as 16.40. So that head loss is given, and you'll be able to calculate here in part B the friction factor F. So part A and B is just substitutions into the energy equation, and then part C and D is where we are looking at the Morrison-Wigert criteria in order to find out the thickness of the boundary layer. And then the final part is maybe trying to determine what the pipe is made out of based on the Reynolds number, the friction factor, and the relative roughness. So let me pause, give you a chance to start discussing, calculating. I guess we're working from left to right. You're going to be using the energy equation and translate the picture and the word, the statement, into substitutions into the energy equation. Okay, so let me record this. And first step, find this required water surface. So what is the water doing that's in the tank? It's what's responsible for pressurizing the pipe. It's providing enough energy to overcome the flow resistance. And it's providing the velocity head that will remain in the water as it is at the building. So the water elevation is responsible for all of those factors. So we have to find out how high should the Z be to account for them. So you'll notice that I've converted the flow rate from liters per minute into cubic meters per second. Determined the hydraulic radius, converted diameter to meters, just some of these preliminaries that we always do in order to determine the velocity, 4.07 meters per second. Okay, now the problem statement itself tells us what the head loss is, 16.4 meters. And so then if we do all of those substitutions into the required elevation for the tank at 1, if you do include the velocity head, then it would be 72.92 meters. Now if you look at the magnitude of this, 35 meters of elevation is to provide the pressure that's required. 20 meters of that elevation is just simply because this building is on a hill, so the tank has to be at least as high as the hill. So this is the Z. 0.846 meters is the velocity head component, so that's relatively minor. There's not a lot of energy tied up in the velocity head. And then finally, the 16.4 was the head loss. Okay, so collectively, all those combined, 72.9 meters is the required elevation for the tank. Okay, so the next thing it was asking for is what would be the friction factor? And as I suggested we could do on the whiteboard, if you rearrange the equation to calculate the friction factor, then we solve for F in terms of the known H sub F, and then all the other physical characteristics such as the pipe diameter and length and so on. Okay, so this would be a pipe that has a 0.0194 friction factor. The thickness of the boundary layer. Okay, now the way that we're going to get there, remember that we have to know the shear stress in order to calculate the shear velocity. And so to get the shear stress, that will be based on the slope of the energy grade line. And the slope of the energy grade line is defined as the head loss due to pipe friction divided by the pipe length. So we'll start with this, then move on to shear stress, then the shear velocity, and finally we can substitute that into the Morris and Wigert equation. Okay, so first of all, the slope of the energy grade line, head loss divided by the length, so 0.0656. So remember we talked about how in a pipe the slope of the energy grade line can be independent of the pipe slope or even the ground slope, that in a way that open channel flow can't be independent. But in a pipe you could have a pipe that's going uphill but a energy grade line slope that's going downhill. So here we've calculated the slope of the energy grade line and then substitute that into the shear stress equation. So the shear stress is 40.2 newtons per meter squared. And then for this fluid, which has a density of 1,000 kilograms per cubic meter, the shear velocity is 0.2 meters per second. So we've normalized the shear stress by dividing by the density and took the square root. 0.2 meters per second is the shear velocity. And then our last step will be to substitute that shear velocity into this Morris and Wigert criteria along with the kinematic viscosity of the fluid. So in the numerator, it's 11.6 times the kinematic viscosity. Denominator, the shear velocity. So we get that the layer thickness is going to be 5.8 times 10 to the 5th meters, meaning that the thickness of the laminar sublayer is 0.058 millimeters. So it's pretty small. Any questions about that so far? Josie?
Can you go over how you did the R?
R, yes, hydraulic radius. For a pipe that's flowing full, it's the diameter divided by 4. That's it. Or if you prefer more complexity, hydraulic radius is the area divided by the wetted perimeter. So you could substitute in pi d squared divided by 4 and then divide by pi d. But effectively, what that leaves you with is d divided by 4 for a circular pipe. Very good. Other questions? It's a 1:50. We're out of time. I was going to go through and show you how we could tell what kind of pipe this is. We'll pick up on this on Wednesday. Maybe a little bit of detective work to find out, was that a concrete pipe, was it a steel pipe, and so on. But you've done what you need, you've learned what you need to learn in order to do the assignment. So have a good weekend. Hope you don't get too snowy. I think we're getting a storm. So I'll see you Wednesday.